What is the minimum number of electrons in chlorine that can have a spin quantum number with the value m sub s equals -1/2? Assume chlorine is in its ground state. So I already wrote out the electron configuration for chlorine. I'm not going to go over how to do that, but you can just use the periodic table to figure that out. And so now I'm going to actually draw the boxes that have the electrons in them because I think that's the easiest way to approach this problem. So for 1s, we just have one box. Same for 2s. Our p orbitals are going to have 3. And each box corresponds to a m sub l value. So that's how we know how many to draw for each one. Then we have 3s, and then we have 3p. And now we're just going to fill in the electrons. So it's 2 per box, and they have to have opposite spins. So these are all full until we get to this last one. So it's 3p5, so we're not quite full. So we have 1, 2, 3, 4, 5. And so it's asking for the minimum number of electrons that can have a n sub s value of -1/2. So in each box, each electron is going to have a -1/2 spin, and the other one's going to have a +1/2 spin. And it doesn't matter like which arrow we assign to which, we just know they're opposite. So in this first box, we know one has to have a -1/2 spin, one from this box, one from each of these 3 boxes. So we're going to get 3 from 2p, 1 from 3s, and then we get to our last 3p orbital, which is not filled. So we know in these first 2 filled subshells that we're going to have to get 1 from each of these. And then we get to this last one. And so this could either be a +1/2 spin or a negative. And the thing is, we don't know. There's no way of knowing. It doesn't matter which way we draw the arrows or anything. So since in this question it's asking for the minimum, since we don't know, we are going to assume that this has a +1/2 spin. So we're only going to get 2 from this one. If it asks for maximum, that's when you do assume it has the spin you're looking for, but it's assuming, or it's asking for minimum. So we can only assume that we're going to get it from these 2, and then this is a +1/2 spin. So we just add up how many we get from each box. That's why I think it's useful to keep a little tally underneath. So 1, 2, 3, 4, 5, 6, 7, 8. So our answer is 8 electrons, and that's all there is to it. Okay, so this next problem is really similar. It's just dealing with a different quantum number. So it just says, what is the maximum number of electrons in iron that can have a quantum number of m sub l equals -1? So I'm going to do the same thing, draw out the boxes, and I'm also going to write their m sub l values below them because that'll help them, or help us at the end of this problem. So s orbitals always have an m sub l value of 0. P orbitals have 3 m sub l values, which again, why there is 3 boxes, and they're -1, 0, and +1. And we could really assign any of these boxes to any of these 3 quantum numbers. It doesn't matter because they are all degenerate. So within a subshell, all 3 of these boxes will be degenerate, which means they have the same energy. So that's why you can assign any number to any box. It's kind of like the electron spin that we did in the first example. So then we have 3s, and that's again 0. We have 3p, which has -1, 0, +1. We have 4s, and we have 3d, which has 5 boxes in a d orbital, because there's 5 quantum numbers ranging from -2, -1, 0, +1, and +2. And now we're just going to fill in the boxes again. Remember that 1 goes in each before they pair up. And then we get to this last one, which is 3d6. So 1, 2, 3, 4, 5, 6. And that last electron really could go in any of these because, again, they are all equal in energy. And so that is going to come into play when we're determining the minimum and maximum. So it's asking for m sub l is -1. So we don't count any from the s orbitals. Coming to the p, we have one box that has 2 electrons for -1, another 2 from 3p, and then we get to 3d. So just because this box is labeled -1 doesn't mean that this is what we look at. So we have to take these as a collective whole and remember that any of these technically could be -1. And since it's asking for the maximum number, we want to assume that this one is actually an m sub l value of -1. So that's why we count for the 2. And then we just add them all up. So we have 2, 4, and 6. So our answer to this problem is there is a maximum of 6 electrons that could be in have a quantum number of m sub l equals -1.